Hey everybody, welcome to Question Barn, the show where I answer your questions. If you've got questions, email them to me at TIPHYT or TIEFighter at titaniumphysics.com. So today, our wonderful guest is Katie Mack. Hey Katie Mack, Dr. Katie Mack.
Hello, how are you?
Yeah, you guys know her. She's famous from the internet and stuff. She's been on several of our shows in the past. Everything's cool. And hey, Katie Mack, you're in the States right now. What brings you stateside?
Well, I just finished up at the American Astronomical Society annual meeting, and that was a lot of fun.
Did you learn anything groundbreaking? Is there anything crazy going on in the world of astronomy?
Well, I mean, there's a lot going on in astronomy, as there always is. There were a lot of really good talks, and there's some interesting press releases and things. I'm not sure that there's anything that I would say is like a super revolutionary thing, but there's some really cool new space missions happening. There's the new star X-ray satellite that's doing cool stuff, and there's a bunch of missions looking at planets and things in our solar system, and comets and stuff like that, and that's really fun. And we're still trying to figure out what dark matter is. There was a lot of talk at the meeting about dark matter and trying to figure out what it is and figure out some problems that might be happening with dark matter theories. So, yeah, it was a lot of fun. I mean, the American Astronomical Society meeting is a massive, massive meeting of 2,000 or 3,000 astronomers all in one place, and so it's just huge, and you see everybody, and you get to catch up with people you haven't seen in years, and so it's kind of a lot more for catching up and talking to people one-on-one than it is really for the talks themselves, I think.
Nice. Yeah, conferences are really fun. I haven't gone to a conference in a while, but they were so much fun because I get to listen to other people's research and then talk to other... Yeah, I don't know. Yeah, so our audience probably knows the life of an academic, even if you're in a department, it's still a little bit solitary because usually there are only a few people within shouting distance who have any idea of what you're talking about. So these conferences are great because you can go to a place where, a dozen people know what you're talking about and you can tell what they're talking about. A lot of times I go to a talk on math or a talk on physics, and I will understand very little of what they have to say past the first slide. So yeah, you can go to these things and you understand, well, not everything, but you understand a ton, and it's really exciting. And you get to see what everybody else is doing without having to read anything.
Yeah, I mean, you get to listen to a bunch of talks, and you get to corner people and say, hey, I heard you were working on this thing. Can you tell me more about it? And you get to say, hey, I'm working on something similar. Let's talk about how we can collaborate. So all of that is really useful.
Yeah, nice. All right. Yeah. Well, yeah. Okay. What's going on in my life? Nothing. I don't know. The academic term started. I'm teaching 3 classes. It's busy. Math, physics, lots of fun. Anyway. All right. Let's talk about the question, because the question is really cool, and I don't want to waste any more time talking about my stupid life. Okay. So here's the question. It's from Bob. He goes, hello again, Ben. We've had previous correspondence. Hello again, Ben. I found and listened to QB episodes, Question Barn. Thanks for the help locating them, because he wanted to figure out where they are. I didn't put them on the website. I only had them on the iTunes feed. And funnily enough, how did it go? I figured, almost everybody listens to podcasts through their iPhone. But then when I started looking at the data, 1,000 of our listeners, and so that's a pretty big percentage of our listeners, 10% or more of our listeners listen to it by going to the website or taking what's it called, reader, one of those simple distribution. Anyway, so moral of the story is I put them on the website too, and then we got 2,000 downloads in a day, and I'm like, oh, wow. There you go. Okay, so switch. Okay. So he's got a couple questions. We'll see how many we can get through. The first question, and it's actually a pretty good one. How do we know that all the matter in the universe came from the Big Bang? His second question is, how do we know that the Big Bang did not expand into an existing precursor universe? It seems plausible to me, and it may be the case. Yeah, we kind of get it. What are we expanding into? And the third one has something about wave function of particles. We'll see if we get there. I don't know if there's enough time. All right, first question. Katie.
Yes.
How do we know that all the matter in the universe came from the Big Bang?
Well, so at this point, we have to define Big Bang, and this is where it gets tricky. So most people think about Big Bang, they think about the Big Bang Singularity, which is the idea that everything was in an infinitesimally small point and it expanded out of that. And that's one idea of the Big Bang, which is probably what the questioner is asking about. But usually when we say Big Bang, we mean the hot Big Bang, which is really just the idea that the universe was hot and small and dense in the past. Like, so distances between things now are larger than they were at the early universe. And so we can extrapolate the expansion of the universe back in time and see that the universe must have been smaller and closer together and more dense in the past. And that's kind of straightforward. Like, so we know that everything in our universe now was at some point in this hotter, more dense state. And so whatever is here now must have been there then, but, closer together. If we talk about the Big Bang Singularity, though, that's a trickier question. I think that the more sort of interesting answer to this question would be to talk about inflation. So inflation is this idea that in the very early universe, the universe expanded really quickly, and then at some point the expansion slowed down, and we got just the kind of normal expansion we have now. And our theories of inflation generally have inflation is caused by the sort of evolution of a field called the inflaton field. So it's inflation caused by the inflaton. And this field changes over time. It's one of these scalar fields, which means it has a value at every point in space. The Higgs field is the same kind of thing.
Yeah, as opposed to a vector field or something.
Right. So it doesn't have like a direction, but it's just like if you tell me a point in space, that point has a value in this field. So it means that, whatever the inflaton is, you give me a coordinate and I can say, well, the value of the inflaton at that point is whatever. It's uniform through, most of our horizon volume, right?
It's like having something that can only where all you need to do to define it is describe the density at every point.
Yeah,
it's not like it's moving anywhere or sloshing. It just there's this much here and there's this much there.
Right, exactly. And so most of the time when we talk about inflation theories, we say that inflation happened because of the evolution of this field, like the field had a different value at early times, and that caused the universe to expand really, really quickly, and then the field evolved to a smaller value, and now the expansion isn't going crazy anymore. And basically, we think that if inflation happened, all matter and sort of all the stuff in the universe, all the matter and particles and energy and stuff, sort of came out of that inflaton field. So as the inflaton evolved to a lower value, it evolved in such a way that it created lots of particles and lots of energy, or not, creating energy, but like creating stuff that is in the sort of standard model of particle physics, and like populated the universe with particles and radiation and matter. And so we kind of need all of the matter in the universe to come out of that inflaton evolution in order for everything to be sort of consistent. There's kind of nowhere else it can go. If the universe was inflating at some point and it was mediated by this inflaton evolution, then you had this really, really empty universe. So it kind of it stretched everything out. So there was really nothing in the universe aside from the inflaton field, because everything else was like just diluted incredibly much by the universe expanding so fast. And so the only thing left in the universe was the energy density of this field. And so everything had to come out of that. And that's actually one of the reasons why we think that dark matter has to have some kind of particle interaction with regular matter, because dark matter has to have come out of the inflaton too, probably. And so whatever dark matter is, we know it doesn't interact with light, but it has to interact with something, or else it would be really hard to create at the beginning of the universe. So we think everything came out of that inflaton, and everything had to have come out of the same, like, sort of energy density of this field that was pervading the whole universe.
Yeah. Okay. So let's unpack what you said a little bit. First off, the listeners might you might remember Bicep 2, the big detector announcement where they were talking about what swirls in the cosmological background. So that happened this spring. We released a show about it. The big exciting thing about it is that if it comes out true, there's new data about whether or not those particular swirls were caused by dust in the galaxy. But if it did come true, if the signal was as strong as we anticipated that it was back then, whether or not it is in the future, it might be wrong. But if it did, we were all excited because it was direct evidence for the inflaton, for the inflation of the universe.
Right. So and those ripples in the cosmological background, if they were real, were produced by fluctuations in the inflaton field. And so we don't know if they're real. We're still looking for evidence of gravitational waves in the early universe, and those are those swirls, that we would see those as swirls in the microwave background. We don't know if they're out there, but we're looking, and if we do see them, then that's evidence that this inflaton field existed and fluctuated in a sort of quantum mechanical way.
So this original question, how do we know all the matter in the universe came from the Big Bang? It's an interesting question because one of the things that we need to get past is the fact that there's nothing permanent about like an atom, right? An atom is made out of its constituent parts, but each of those, fundamental particles is kind of an excitation in a field. They pop in and out of existence depending on how much energy you have smashing together. So you can make an electron by smashing two gamma rays together just the right way, or two high energy particles. An electron might pop out of that. So will a positron, an anti-electron, right? So you'll get positron electron production. So the question isn't, did all of the electrons in our universe come from the Big Bang? Because the answer for all of the matter is probably not. If I decide to zoom my God camera in on an electron and follow its life back to the early days in the universe, chances are it was produced at a time after the Big Bang singularity.
Well, everything, yeah. I mean, if you're talking about the singularity, there was no time except after. Right?
Yeah. I mean, aside from fundamental truths of general relativity, like you wouldn't even get close to that Big Bang. The electron you follow back in time would probably be produced in the first, little while after the gluons were made. Two things smashed together and pop this baby electron, and it's been wandering around the universe ever since. And the same thing for, pretty much all the stuff in the universe. It was produced at some time. Some of it probably even came about from some nuclear reaction that took place, within the lifetime of the Earth. So, it's matter's popping into what we call matter is popping into and out of existence all the time. That said, if you took a little, imagine you were an accountant and you said, okay, somebody exchanged that electron, they changed it back into energy, and that energy went into something else, and you were tracing the money back as time went on. What Katie Mack was saying is that, I keep calling you Katie Mack because that's what your name is on Twitter. I'm sorry, Katie.
That's fine. You can call me. A lot of people call me Katie Mack like it's just one word. It's fine.
All right. So what Katie was saying with all the fields and stuff is that if you were one of these accountants, you were following the energy back, your electron that you're following around, at some point in time it got created, and that energy came from somewhere, and you could track that energy as it goes back and back and back until probably the standard picture that cosmologists are using in terms of the story of the universe right now is that there was a time when probably all of the energy in the universe was locked up in this inflaton field. And then afterwards, as the inflatons stretched out the universe, and all these things happened, blah, blah, blah. As a result, all of the matter came about from various energy reactions, popping into existence at some point in time.
Yeah, and it might be worth specifying that if we're talking about the hot Big Bang, which is like, the time when the universe was hot and dense, anything before the cosmological background, basically, which is only like that's 380,000 years after the Big Bang, so not really close to the beginning at all, except relative to now. If we're talking about the hot Big Bang, then most of the matter, like the most of the particles in the universe, would have existed then. And so those particles, like, so everything, all the matter, even in terms of the individual particles, a lot of the matter that we see today was around during the hot Big Bang. And so it's been changing over time. I mean, if we talk about atoms, like nuclei of atoms, then still most of the nuclei in the universe are hydrogen, and that comes from the Big Bang. That was all formed in the hot Big Bang. If we talk about heavier atoms, heavier nuclei, like, you know, gold and I don't know, rubidium or whatever,
Yeah.
a lot of those things come out of stellar processes.
Yeah.
So there are only a few atoms that were formed during what we call Big Bang nucleosynthesis, which is the formation of the first few like bound nuclei, and that's, you know, hydrogen, helium, a little bit of lithium and beryllium and that kind of stuff, like tiny little amounts of that, mostly hydrogen and helium. Everything else was formed in stars. So if you want to know where the matter came from in terms of like the atoms, a lot of that comes from stars.
Yeah. Yeah. Actually, so there's actually kind of a whimsical answer to his question at more fundamental in terms of like, so earlier you corrected me when we were talking about time existing at the first singularity, right?
Right.
So one of the reasons we say that, so let's say you were this accountant following the packets of energy until through their origin from one type of particle down into an electron, etc. Okay.
Mm-hmm. Yeah.
If you followed the world line of that packet of energy, as if this concept that I'm describing meant anything, if you followed this world line back and back and back in time, the Big Bang is a certain specific type of singularity in general relativity. It's called a Spacelike Singularity, and that means that it happened all at once everywhere. And this particular type of singularity means that if you follow anything back in time, if you can keep following the history of an object back and back in time with no end, it's destined to hit that thing. So all of the energy in the universe was destined to, you can trace it all the way back to this space-like singularity. And it's interesting because there's one way you can get new packets of energy, new world lines of energy into the universe without starting at that place. Stephen Hawking, baby. It's closed time like curves. So if there's a time machine going in a loop somewhere in the universe, new packets of energy can come out of that never originated at the Big Bang. Like, I don't know, that's pretty Futurama stuff.
Okay.
But don't worry about that. Like that's a little bit science fiction-y.
So if we break the laws of physics as we know them, then yes, you can get matter that doesn't come from the Big Bang.
Yeah, if you look at Stephen Hawking's textbook on space-time, you can...
Is this the large-scale structure of space-time?
Yeah.
Okay.
You were reading that recently, weren't you?
Yeah, I was.
Yeah. Did you get to that part?
I didn't read that part. I was reading up more about the GR stuff and black holes. But anyway.
He does weird topology stuff. It's very silly.
Cool.
Okay, Katie, do you want to start talking about number 2? Yeah, we'll just mention this number 2 because it's kind of one of the forefronts of theoretical physics. I'm not sure if you know anything about it. The question was, how do we know that the Big Bang did not expand into a precursor universe?
Right. So this comes into the idea of, you know, if the universe is expanding, what is it expanding into? The idea, I mean, it kind of originates, I think, in the picture of the Big Bang as being an explosion from a single point, which is a lot of the time sort of the way that we describe it. But as you're saying before with the space-like singularities, it's not a single point in a single part of space. It's like every part of space was that point, you know. And so it's not like we were like inside this larger thing and we exploded out of one part of that larger thing. It's like all of our dimensions like came into existence and, you know, spread out from an early, you know, from like not being there before. Like the dimensions themselves, not just like extent, like stuff in those directions, but the actual space-time. I mean, there are a lot of different theories where our universe exists in a larger dimensional space. for instance, has an idea where you have sort of like two parallel spacetimes that like come together at some point and come apart like these. So picture sort of two sheets of paper parallel to each other, and they come together like clapping, and then they come apart again. And each time they come together, that's like a big bang. And we live on one of those sheets of paper, and that sheet of paper represents like all three of our spatial dimensions collapsed into, like 2 dimensions. And the space between the sheets of paper represents another dimension that's beyond our dimensions. And so those collisions represent the Big Bang. But an important thing thinking about that is those collisions are like happening at every part of that sheet of paper at once, right? So it's really not like that those sheets of paper are like collapsing into single points in order to do the Big Bang. Just you can have an infinite universe that still has a Big Bang at every point, sort of like.
Yeah. So I think so imagine that. Yeah. So in these things, they're like, okay, so if you use the sheet of paper analog, it's like that's a space-time. So we're stuck on our space and time coordinates are stuck on this sheet. It's kind of like, you go to the supermarket and they have those rolls of bags, the plastic bags, and you like tear one off. That's essentially the shape they're imagining. You got these two universes that get crimped together at certain points. And so all across the length of the universe, at one time, it'll be crimped to another universe, and that's the Big Bang. There's another theory that's interesting. So the picture of the Big Bang is happening everywhere at once. That's like this orthodox general relativity picture. It's one I subscribe to, by the way. I'm pretty boring. But various theoretical physicists are trying to broaden the horizon of physics, and there's a variety of coincidences in cosmology that people aren't quite sure if they're coincidences, if they're supposed to be that way, or if it's just a lucky coincidence, or what the deal is. I think they call this genre of analyzing things, they call them like multiverses, and they're not multiverses. Like I would describe the thing Katie was just explaining with the two universes side by side crumping together every once in a while. I would describe those two separate universes as being two different, a multiverse of different sheet universes. But the name multiverse has kind of been stolen away by another group who imagine that our universe, the Big Bang didn't happen everywhere in our universe all at the same time. What they imagine is there was a local region that had this inflation effect, and there's a much larger space around us. They call it the multiverse, full of little collapsing universes that just kind of bubble out of it. Isn't it? It's called like the eternal expansion theory or something. Eternal inflation.
So you're talking about eternal inflation. Yeah. So that's saying that that's talking about different hot Big Bangs rather than different singularities, which is totally possible. That's totally possible. I mean, because so imagine that inflation starts going on in the universe. Okay. And it goes on for a while, and then at some point, this field, like the value of this field becomes such that inflation stops and the expansion slows down, right? The value of the field can be different in different parts of the universe because these are different. The universe is expanding so fast that different parts of the universe are now not causally connected to each other. So, like one part of the universe doesn't necessarily know what's going on in the other part of the universe. So there's nothing to keep the value of the inflaton field the same everywhere. Which means that it's possible that the inflaton can evolve to a smaller state in one part of the universe, which means that inflation will stop over there, but keep going somewhere else. Like the inflaton doesn't evolve to that lower state in this other part of the universe. And so if you think about it, like all the places where inflation is still going on, those parts of the universe are expanding exponentially. And even if inflation stops in certain pockets, there's still like a much larger space where inflation is still going on, because that part of the space is expanding a lot. And so this is what eternal inflation means, is like every part of the universe, you're getting like little pocket universes, which are places where inflation has stopped and the hot Big Bang has started happening because the inflaton field has evolved into all the particles and stuff we know about. So there are little pockets in the universe where inflation has stopped, but there's also larger spaces where inflation is still going on. And so you get these really isolated parts of the universe where inflation has stopped. And each of those is causally disconnected from every other one. They can't communicate with each other. They're just way too far away. And so those are, in a very practical sense, separate universes, even if they all came out of the same sort of, the expansion of the same kind of region of space. And so like, there are lots of little hot Big Bangs in different parts of the universe in this scenario. But in terms of like the Big Bang singularity, if you talk about that, that's a totally different question. Mm-hmm. And that's where you get, this sort of spacelike singularity issue,
right?
Where it's, you have to be complicated to find a way for that to happen, in some other pre-existing space. But in terms of hot Big Bangs, in terms of like universes that look like our universe, there could be tons of them, or they could look different from our universe. They could have different properties. And that's one of the things that people talk about when they talk about the multiverse, is this idea that, it's not that there are really distinct universes in the sense of like being like in a totally different like dimension or something like that. They're just really far away. And so we talk about our observable universe being anything that we could in principle communicate with, because it's close enough that light could get to it, and or light could get from it to us, in the time that the universe has existed. These other universes would be beyond that. They'd be beyond our horizon. It would be in principle completely impossible to ever have any contact with them for them to have any effect on us.
Right.
So that's an idea of the multiverse that can come out of this inflation idea, and that's eternal inflation. And it's a tricky thing. Some people say that eternal inflation is a complete, direct consequence of the idea that inflation happens at all. Just because, like I said, if you have inflation happening, like if the inflaton field can take different values in different parts of the universe, there could always be some part of the universe that's still inflating, and that would just make space really big, and you could have all these other universes happening somewhere else. So maybe eternal inflation is just a complete, like, logical consequence of the idea that inflation happened at all. There might be ways around it. It might be that inflation didn't happen, and so you don't have to worry about internal inflation at all. So, there are sort of different ideas about this, but that's one way to get, like, lots of little Big Bangs, but they're hot Big Bangs, not Big Bang singularities.
Oh, hey, I misunderstood the fundamental nature of the thing. Oh, okay, that's good. That makes sense.
Okay.
Well, there was one. Do you know if there's still other people are still researching the possibility of the universe, instead of being expanding, that it's all just a local bubble that's contracting in on itself, and we're near the center of it? Have you heard that one?
I've not heard that one. Is this an idea about trying to get rid of dark energy with?
Yeah, that's right. I think Ellis and his group were working on it in South Africa, but I don't know. That's pretty old info.
We'd still have to be expanding, but the accelerated expansion, so dark energy is a different kind of basic idea that the universe is expanding really fast. So there's an idea that maybe the accelerated expansion isn't happening, and instead we're just like in the center of a big void, and so it looks like things are moving away from us in a weird way. Mm-hmm. It's actually really, really, really hard to set that up to make that work, and I don't think it does work. I think that basically you'd have to be at the dead center of something really strange, and there's really no reason we should be, because we're not that special, and it's also really hard to get even that scenario to match with observations. So it really does seem like the accelerated expansion is just happening everywhere.
Yeah. No, well, I mean, like I said, I don't believe any of this crazy nonsense that isn't lambda cold dark matter. but
Yeah.
it's fun to talk about. I mean, yeah,
Sure, yeah.
I think I appreciate that there are physicists who, I mean, the lambda cold dark matter general relativity picture is founded on some very specific, very simple assumptions. And lots of these consequential theories come about when people try to modify or question one of those assumptions. And so, I mean, I think it's bananas, but I think the practice of questioning these things is good. So
Yeah, definitely.
if one of them is right 30 years down the road, then I'll eat crow. I'm glad they're doing it.
Yeah.
I don't know what to say. There's lots of weird ideas out there. I'm glad people are smarter than me are working on it. All right. Well, that's probably it for today, right?
Okay. Yeah. That sounds good.
Thank you, Katie. Thank you, Bob Whiteman. So everybody, you can follow Katie Mack on Twitter. Is there anything else you want to pitch, Katie?
Well, no, I mean, I'm on Twitter at AstroKatie. I'm on Facebook at facebook.com/AstroKatie. If you go to my webpage, which is predictably astrokatie.com, there's other information about stuff I've written or where to find videos that I've done and stuff like that. I've got a few sort of video things going on, a couple of podcast things. So, check it out, see what's out there. Or just, tweet me if you have more questions.
Katie Mack is one of the most prominent Twitter outreach scientists in the world right now. Way to go, Katie Mack.
Thanks.
All right. Well, okay. So, hey guys, I'm going to close out the show tonight. Now, if you want to send me questions, I've got a big stack of questions. I like working through them and inviting people to talk about them. Send it to TIPHYTER at titaniumphysics.com. TIE Fighter at titaniumphysics.com. All right, everybody. Keep science in your heart. All that jazz. Bye.